Hello students, and welcome to lecture 3 of mechanics of materials. In this lecture we are going to discuss the shear stress and shear strain. In previous lecture we talked about the normal stress and normal strain and some tensile and compressive loadings, where our force in that case was actually perpendicular to the cross section area of the body. Let's say this is the cross section area of equal to A, okay, and we had the force applied that was actually perpendicular to that cross section area. So we said that the stress would be equal to the force divided by area, or force per unit area, and this was our normal stress. And then obviously the strain was produced, which was the normal strain, and we represented it as epsilon, which was the change in length divided by the original length of the body. Okay, so this was the previous formulas that we used for the normal stress, but in this case is a little bit different in a sense that, let's say we have a body 1 and we have body 2, okay, and they are attached by some glue, and you are trying to pull them apart with the force V applied. Okay, so V is usually force is represented with F. When you have a shear force, we try to represent it as V. Okay, and they have a contact region A, so these bodies are attached at a contact region of A. Okay, so our stress in this case would be slightly different in a sense that now the forces are applied to this contact region that is trying to slide the area, one area over the other. Okay, so those forces are actually parallel to that contact region, and when this is the case, when the forces are parallel instead of perpendicular, we have the shear stress induced. And as you can see from the definition, that shear stress is tangential force, so it is tangent to the area. Okay, so it is tangent means it is parallel to the area, acting parallel to the surface. So whatever the surface area is, the forces are acting parallel. For example, this one and this one, they are trying to slide one area over the other, and the stress induced is the shear stress, represented as tau, and the formula is the same, force per unit area. Okay, so this is the basic concept of our shear stress that we are going to discuss in the coming slides. Difference is that the normal stress is in the normal stress, force is perpendicular to the cross section area. In shear stress, the force is actually parallel to the cross section area. Okay, for instance, you have this body with the initial height of h, and you have a cross sectional area of a. Okay, and when you have this initial state and then you apply some force here, okay, you apply some force here, what happens is it tries to deflect the body. And imagine this body consists of multiple layers, just like this one, body 1 and body 2. In this case, let's say this is body 1, 2, 3, 4. Okay, let's assume that. So when this is the case, what happens is that the forces that are applied to these layers are actually parallel to those cross-sectional areas. So let's say each one is a cross-sectional area, okay, and these cross-sectional area are experiencing some forces, but the forces are parallel. So the top would be in this direction, the bottom would be trying to move in this direction, and then those layers will slide over each other. So the forces applied are actually parallel to those cross-sectional area, and that is why you are getting some deflection, the resultant deflection x. Okay, so when this is the case, the stress is induced, or the shear stresses. Now imagine a body with a fixed base, and you apply a force that is parallel to the area on the top, and the body gets deflected. Okay, since it is not moving at the base, the top region moves, and you get a deflection that is linear from top to bottom, meaning it keeps on increasing from the top to bottom. Okay, and the result that you get is let's say its height is L, the initial height, and then you deflect it by delta x, so that is the final or maximum deflection that you got. And you got two things as a result of that. One is the angle theta, okay, and then if you look at it, the length and delta x are actually perpendicular to each other, and this actually helps us calculate the shear strain, because we know the shear stress now, because the shear stress would be the force applied to the divided by the area that is parallel to the force. So that would be the stress. Now if you want to know the shear strain, then this L delta x and this angle theta will help us calculate the shear strain. and it is represented as gamma. The shear strain is represented as gamma, and it is actually the maximum deflection delta x divided by the original length. Okay, so that is our shear strain. So the more the deflection, the more will be the strain. In other words, it is the change in the length divided by the original length, although it is a little slightly different, because it is in case of shear, it will be the change will be actually parallel to the area. In previous cases, the change was actually perpendicular to the area. Okay, now this is represented by the gamma, that is the shear strain. Now if you look at this, so this is actually giving you an angle theta here, and theta in this sense, we know that theta, if you take this theta, so the delta x is actually perpendicular, and then the L is parallel to, or adjacent to the theta. So you can actually use the tangent of theta. So tangent of theta is in this case equal to the perpendicular delta x divided by the base, which is L. Okay, so if you remember, tangent theta is equal to perpendicular divided base. So perpendicular is delta x, base is L. Okay, it is the same thing as this one. Okay, and that is why we can say that your the shear strain will also be equal to tangent of theta. Okay, I hope that makes sense. Now let's solve a problem. It's a very basic problem, and says that determine the shear strain produced in the body. Now this is our problem. What we want to do is determine the shear strain. We already know the formulas, so in this case what we have is we have the L, okay, this one, which is actually 8 meter, and then we have delta x, which is actually what, 3 meter. That is the change that is produced in the body, 3 millimeter. Just keep the units in mind. And then you have the angle theta. Okay, so delta x, and you have an angle theta that is actually in this case unknown. So because to know the shear strain, we need to know either these two, or we need to know the theta. So if we know either these two, or we know the theta, we can actually calculate the shear strain. So in this case we know the other two, so our shear strain will be equal to delta x divided by L. Delta x is 3 millimeters, so I will convert it into meters, so to keep the units, or you can just keep everything in millimeter, that's even better. So you have 3 millimeter delta x divided by 8 meters, so that is actually 8,000 millimeter. So keeping things very simple, so our shear strain will be equal to, let me get my calculator. So you have 3 divided by 8,000, and it gives you around 0.000375. So you get 0.000375. Obviously it will have no units because millimeter and millimeter cancel out, so you will have the strain of this one. Now if the question says also find out what would be this angle, so it's again very easy. Either you can use the strain value and find out the theta using this equation. So it would be gamma is equal to tangent of theta, and you can actually put the tangent of theta is equal to 0.000375, and you get the theta is equal to tangent inverse of okay, so you can do that. Theta is equal to tangent inverse of, so you get tan inverse and then 0.000375. okay, so that is around 0.021 degree. Okay, fair enough, and then we can maybe in the next lecture go on with more details of shear stress and strain, and specifically involving the torsion. Alright, see you in the next lecture. Take care. Bye.